In this example, we are going to show that p bar dot p plus q implies q is a tautology. There are two propositions in this statement. So what I've done is I've taken q and written down its values one at a time. So we've 0, 1, 0, 1, as you've seen before, and take p's values two at a time. So we've two zeros followed by two ones. So we'll have four rows. That covers all the combinations for propositions p and q. P bar, or not p, is got by negating the values of the p column, so we get 1, 1, 0, 0. We also need p plus q, which means p or q. Remember, p or q is false, that is 0, when both p and q are false. When they're both zeros, then p plus q is 0. Otherwise, we have ones. Now let's look at the left-hand side of this implication. That is p bar dot p plus q. P bar and p plus q is true only when both p bar and p plus q are true. So that happens here. P bar is 1 here and p or q is 1 here. So p bar dot p plus q is 1. And it's 0 for the other values because we have the zeros appearing here, 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 and here. Now at last we can get the column of values for our statement that we're trying to show is a tautology. So hopefully we'll get all ones here. So p bar dot p plus q implies q is false only when the left hand side, that is all of this here, is true, and the right hand side, that is q, is false. So if this is 1 and if q is 0, then this statement yields 0. So we have the 1, 0, 0 situation that I explained about earlier. So we can see when p bar is 1, as it is here, and when this here is 1, as it is here, p bar dot p plus q is 1, and the right hand side of the implication statement is 0. The right hand side is q. Well, it's 1 here, so we don't actually get a 0, we get a 1 here. So when the left hand side is 1 and the right hand side is 1, then the entire statement is true, we get a 1. And it's vacuously true when the left hand side is 0. So when the left hand side of the implication statement is 0, it doesn't matter what q is, then the entire statement is true. So we don't have this, we don't have a false value here. So we've all true values, all ones in this column, which shows that our statement is a tautology. In this example, we are going to look at the propositions p plus q bar and p bar dot q bar. We're going to show that they are logical equivalents by looking at the truth table. So there are two. This proposition is built up of two propositions p and q. So we're going to have a truth table with 4 rows. So let's say we take q and we write down its value 0, 1, 0, 1, and then p as 0, 0, 1, 1, as you've seen before. Let's look at p plus q, that means p or q. That is false when both p and q are zeros. It's true when at least one of p and q is a 1, as it is for the next 3 rows. We have ones here. To negate this, we just flip these values, the 0 to the 1, and the 1s become zeros. To get not p or p bar, we flip the values of p, so the zeros, 2 zeros up here become 1s here, and 2 1s down here become zeros. Similarly for not q, q is 0, so not q is 1 when q is 1, not q is 0, and so on. Let's look at not p and not q. Not p and not q is true only when both not p and not q are true. When both not p and not q are 1s, then not p and not q is 1. So that only happens here for this row. And for these 3 rows, we have zeros. We can see that this column is the same as this column here. The 2 columns are identical. So that tells us that the propositions not p or q and not p and not q are equivalent. They're logically equivalent. Let's look at the biconditional truth table. This symbol here, the double arrow symbol, means if and only if. which is often shortened to IFF. So we would read this as P if and only if Q. This is true only when P implies Q and Q implies P are true. This should be just an implication. Similarly here, so we just have single arrowheads here. So P implies Q and Q implies P must both be true for the biconditional P if and only if Q to be true. So here's the truth table for P if and only if Q. We have 4 rows, of course, because it's built up from 2 propositions. We have 0, 1, 0, 1 here, 0, 0, 1, 1. So P if and only if Q is true when either both P and Q are true, as they are, as you can see in this last row, or actually if both P and Q are false. So if both P and Q are 1s, or if both P and Q are 0s, then P if and only if Q is true, is 1. Otherwise it's 0. In this example we are going to look at the propositions P if and only if Q and not P or Q are logically equivalent. So we need columns for P and Q, of course. So we'll have 4 rows. We need a column for not P. We just negate all the P values. When P is 0, not P is 1, and vice versa. P is 1, not P is 0. We need a column for not P or Q. Not P or Q is 1 when either not P is 1 or Q is 1. So we're going to get 1 here for these 2 rows. The exception here is 0 here, because both of them are 0, and 1 for the 4th row. Now we need a column for P if and only if Q, or IFF P if Q, as in if and only if Q. So P if and only if Q is true when both P and Q are true, or when both P and Q are false. So if we look here in this first row, both P and Q are false, so P if and only if Q is true, is 1. And in the last row, you can see that both P and Q are true, so P if and only if Q is true, otherwise it's 0. You can see, by the way, that these 2 columns are different, which tells us that the propositions P if Q and not P or Q are not logically equivalent. In this example, I want to go back to the biconditional truth table for the propositions P and Q that we saw earlier. I just want to explain a bit more about why P implies Q and Q implies P must both be true for P if and only if Q to be true. So the double arrow means if and only if. The single arrow just is the implication operator. The implication operator appeared like this in the examples you saw earlier, but I'm just going to write it as I have it here. Okay, so just to prove this, which I didn't prove before, I'm going to draw out a truth table. So let's look at P implies Q. P implies Q is true if P is false. It doesn't actually matter what Q is. P implies Q is vacuously true if P is false. And it's true if both P and Q are true. It's false if P is true and Q is false. So here's the 1, 0, 0 situation I explained about earlier. Now let's look at Q implies P. If Q is false, then Q implies P is true, as it is for this first row. It's false here as well. And Q implies P is true if Q is true and P is true. And here we have the 1, 0, 0 situation. Q is true, P is false, so Q implies P is false. Now, in this column, we're going to look at the statement P implies Q and Q implies P. So we have the AND operator. So this is true only if both P implies Q and Q implies P are true. So when both of these are 1s, as they are in the first row here, then this proposition is true. And one of them is a 0, then it's false. And when they're both 1s, it's true. So you can see that this column is the column for the biconditional operator, P if and only if Q. So this here is logically equivalent. Well, it's defined to be P if and only if Q. In this example, we are going to look at the proposition P implies Q implies not P dot not Q. So this is built up from two propositions P and Q. Normally in the truth table for P and Q, we would take, say, Q and write 0, 1, 0, 1 down here. And then for P we'd have 0, 0, 1, 1. It hasn't been done here, but it doesn't matter. Let's look at the truth table for P implies Q implies not P and not Q. So I have a column here for Q, so we 0, 1, 0, 1, and a column for P, taking two at a time, 2 zeros and 2 ones, so we have 4 rows. Let's look at P implies Q. P implies Q is true if P is false. P implies Q is vacuously true if P is false. So in the first two rows here, we have ones. P implies Q is true if both P and Q are true. So we have 1, 1, and we have 1 here. And the only time it's false is when P is true and Q is false. So we have 1, 0, 0. Let's look at not Q. We just negate all the values in this column. So the 0 becomes a 1, the 1 becomes a 0, etc. Let's look at P and Q bar. Remember, this can be written like this. It's upside down V. This is the AND operator. P and Q bar is true when both P and Q bar are true. So when both P is 1 and Q bar is 1, then P and Q bar is 1. You'll see that it's 0 for the other values because we have zeros appearing in the other rows for P and Q bar in the first two rows and in the fourth row. Let's look at the negation of P and Q bar, or P and Q bar bar. So we just negate all the values in here. So the 0 becomes 1 and the 1 becomes 0. Finally, we can get to our statement. So here is the P implies Q column. So we're interested in this column implying this column here. So we have the implication operator here. It's true when P implies Q is true and not P and not Q is true. Similarly here, same values here. This implication operator is true if the first part is false. So it's vacuously true in that case. So it's 0 here and we have 0 here. Well, it doesn't matter what this is actually. If the first part of the implication statement is 0, then the entire statement yields true 1. Finally here we have P implies Q is 1 and this value is 1, so we have 1, 1, 1. So we can see actually that this statement here is a tautology because all the values are 1s.